Hello, everybody. I'm going to go through the solution of question 31, algebra section of the course Maths 1151 at UNSW. In this question, we have a line, and we would like to prove that that is parallel to the plane. So we are in the three-dimensional space. We have line equation given by this way, and we have a plane equation given a parametric equation way. And we would like to prove that this line is parallel to this line. So we need to find the parametric form of this line. That's the first thing to do, so we can do our calculations comparatively, so we can do our calculations as vector calculus. In order to be able to find out parametric forms of a line in this form, we say this equal to some parameter lambda. Lambda is any real number here, and we obtain parametric form by doing the each of the equation and obtaining x and y and z. X, y, z's will form a vector in three-dimensional space, and we will be able to write it down this vector as a constant vector plus lambda times another vector. So that was the vector parametric form of the line. From this equation, we have x is equal to x minus 1 over 2 is equal to lambda, gives us x equal to 1 plus 2 lambda. Y over 3 lambda gives us y 3 lambda. And the last equality gives us z z is equal to minus 1 minus lambda. That is that one. So if you look at the coefficients as the constant terms in this three equation, so the general term, the L is the consist of the all vectors in the three-dimensional space, such that this vector is constant term, which are the constant terms in these three equations, which is 1. There's no constant term, that will be 0, and this one will be minus 1. So here, 1, 0, minus 1 is the constant terms. And the coefficients of lambda will be 2, 3, minus 1, 2, 3, minus 1. This is where it's coming from. And the lambda, we should say what is the lambda in this set. Lambda could be any real number. So this is, we know that this is a line equation, vector parametric form of the line equation, such that this line passes through the point 1, 0, minus 1, with the direction vector 2, 3, minus 1. So this line is parallel to this vector 2, 3, 1, 2, 3, minus 1, and it passes the point 1, 0, minus 1. Now we would like to prove that L is parallel to the plane. So we need to define that, because two parallel lines is obvious to understand what is the definition are. But for a line to be parallel to the plane, you need to have a particular definitions for this concept, because a plane is a two-dimensional object in three-dimensional space, and a line is a vector, is a one-dimensional object, has one parameter. So you have one parameter object and you have the two parameters object. How you can possibly compare them algebraically or logically, it is not clear. You need to give a definition. This comes from the theory. Theory tells us how we can observe, how we can understand this. Also, you can think of a geometrical way. You need to think about a plane like a sheet, and you want to think about a line parallel to that sheet, that plane. There are several ways of doing it. Yes, that's true. Several ways of doing it, because you need to maybe think about a plane parallel to each other, or you need to think about how the normal vector and the line interacts each other. And this is the one that we are going to take it here. This is the definition here. This is how we are going to prove the line is parallel to the plane. And also, we need to state this. A line is parallel to plane if the direction vector in direction, the direction vector of the line, orthogonal to the normal vector of the plane. So this is how we take the definition of the line, how line, a one parameter object, can be parallel to a two parameter object in three-dimensional space, is that the directional vector of the line should be orthogonal to the normal vector of the plane. So the normal vector is the vector which is perpendicular to the plane. If you have an orthogonal, if the directional vector is orthogonal to the normal of the plane, then the line and the planes are parallel. Actually, the line is inside a plane which is parallel to that plane. Okay, so this is the definition that we are taking, and we would like to prove that. And the normal vector of P, this is what we need to calculate, because the vector, directional vector, is obvious from this equation, which is this vector, but we don't know, we need to calculate the normal vector of the plane in order to be able to compare to it, in order to be able to check that their dot product is orthogonal. Their dot product is 0, such that they are orthogonal. So in order to be able to calculate the normal vector, you take two directional vectors of the plane and you cross product them, right? So this vector and these vectors are this vector and this vector are directional vectors of P, of the plane P, as we realize that there is no constant term in this plane. So this plane passes through the origin in three-dimensional space. And so this is one of the directional vector. This is another directional vector. And we are going to calculate the cross product of this vector. We have ijk. This is how we calculate the cross product. That was I'm not going through the definition. I'm just I'm doing the calculation here. You can have a look at the definition of the cross product if you don't remember, but hopefully you do remember. ijk here, and ijk is basically the standard basis of the three-dimensional space, 1, 0, 0, 0, 1, 0, 0, 0, 1 vectors. This is this vector, 1, 1, 0, and this is this vector. So we are going to calculate the minors and the determinants of this. The determinant, by the definition of determinant, you will be able to get the coefficients of I by just removing this and this and calculating the determinant of this. So this will be I, and that will be 1 times 1 is minus 1. So we have minus I here. So for the jade column, so this is the jade column, is the first row, second column. So we have a minus 1 here because of the position. The position of the j vector, you have minus 1, and you have first row, second column. So that will be minus 1, right? So there exists a coefficient minus 1 in j. So you're taking out this column and this row, then you have then you're calculating the determinant, this, which is minus 1. But since you have a minus 1 here, that will be plus 1. This is why I have a plus j here, because of the position, because j position is in the negative. This is a very common place that the people confuse. Please be careful, especially if you have this j position. Remember, you need to have minus 1. Remember, you for the j position, you need to have minus 1. You need to multiply that. This is minus 1 in front of the j, right? You have minus 1 times j, and then you have the determinant of 0, -1. Since you know how to do the cross product, and it's another subject, so I don't want to do it very deeply. You're supposed to know how to do the cross product. So that is the cross product. I'm just reminding you here how to do it. For the jth position, you have -1. You're removing the j, this column and this row, and whatever it's left is you calculate the determinant of it. 1 times -1 is -1, but since you have a coefficient -1, this is how I got the plus j. For k, so this is the coefficient is +1 in this case, and the determinant of here, you remove this row, this column in your eyes, and you calculate the determinant here. So it is just this times this minus this times this is 0. So this is 1. So it is just plus k. So in order to be able to write it down, this is the coordinate system writing, and this is the vector writing. So this is equivalent to -1, 1, 1. So this is the normal vector of the plane P. If the L line is parallel to the plane P, then the direction vector of this vector, direction vector of L, is orthogonal to the normal vector, which means that they are perpendicular to each other. Two vectors are perpendicular to each other if their dot product is equal to 0. The only thing that we need to do now is take this directional vector of the line L and take this normal vector of the plane and do the dot product each other. If we get 0, that means that this vector and this vector are perpendicular each other. And that was what was our definition is. That would be proving what we want to prove. So if you do the dot product of these two vectors, you have 2 minus 2. 3 times 1 is +3, 1 minus 1, so we have -3 plus 3, which is 0. So that means u vector and u, which is the directional vector of the line, and this vector n, which is the normal vector of p, are perpendicular together. That implies that the line L is parallel to the p. That's all for this question. Thank you very much.